This is Christine Washburn from Physics. After working through the learning inventory, I made a program map to get an example out there of what this might look like. In this video, I'm just going to walk you through my team's thought process with both the learning inventory and creating the map itself. So I worked with Andrew Vancher from Physics and Eric Natardi from the Tutoring Center. And the inventory starts, as you know, with some reflection on careers students might end up in after completing our program. And in this case, a bachelor's in physics, since there aren't many jobs for physics folks with an associate's degree. Our group discussed this in terms of equity. We didn't necessarily talk about each of these dimensions of equity in the places where the learning inventory was prompting, but we did cover all 5 dimensions in our discussions in various places in the learning inventory and in the map development. Most physics majors don't end up with a job that has the word physics in the title. A bit less than half of the people with a physics degree are going to go straight into a job after their bachelor's, mostly industry. And then the other half or more will go to grad school, sometimes in physics, sometimes in something else. And while physics majors, we knew they went into other fields, when we actually looked at data from third parties, we realized that the overwhelming majority of our physics students are going into non-academic pathways. So here's a graphic from the Society of Physics Students website on careers for people with a bachelor's degree in physics. You can see the word physics only shows up in one job title. When we were thinking about our students' futures, we tried to think beyond just the entry-level job that they might get after they graduate with a bachelor's. We tried to think about where they might be 15 years from now, so that instead of getting them the bare minimum, we're thinking about equipping them to really be lifelong learners who are growing all the time and eventually leading change in their field and in the world. Some of them are going to be looking into entrepreneurship way down the road. Some are going to be in areas totally foreign to us, like economics and patent law and meteorology. We tried to come back to that first step, thinking about careers often as we were doing the learning inventory, so that we were keeping that equitable aspiration and economic progress in mind. We're not advising a bunch of mini versions of ourselves. Our students are going to have radically different career paths from us, and we have to keep that in mind. So in the knowledge, skills, and ability area, we revisited that careers list and we asked ourselves, what do students need to be successful in those careers, and where in the DTA core requirements can they get those knowledge, skills, and abilities? So for example, we all know communication is important, and when we thought about a potential career for a physics major, of course technical writing goes without saying, but most of the people in these careers are going to have to at some point be able to teach themselves something technical. New federal regulations, a new programming language, new technology, or something comparably big. And so we felt it's really important also for them to understand technical reading, how to teach yourself something based on just a text or a website or journal articles. In addition to that, with technical writing, they need to not just be able to communicate technical ideas to their peers, but to non-technical audiences too. They need to be able to do that in writing as well as orally. And we had a bunch of similar discussions for the other distribution requirement areas. Like we discussed how visual communication would be useful to our students because it teaches them to represent abstract concepts graphically, and it can help them be more creative with their problem solving. In addition to that, taking an actual art class could expose them to the peer review process, which is a good thing to have for a scientist. When we got to the hand-pack practices, we had a ton of ideas. In STEM, doing a large project is huge for a lot of reasons. First, it helps really cement the knowledge, and they're applying things and understanding it more deeply. But second, they're going through this cycle of initial idea, prototype, refinement, analysis of the final product, and a written and oral presentation. And that's going to model for them more of what the work cycle will look like when they're in the work world. And it also gives them some really critical group work experience. When our students do a capstone project, that often shows up on their resume later as a way to demonstrate to employers that they have the necessary skills to do a job. And so it's a big contributor to equitable achievement. Super important in physics and in STEM in general is having some kind of undergraduate research experience or an internship. And this is where the conversation started to branch out, because we realized this is not something we can support here. So we need to figure out where in our advising process we want to start the conversation with students on how to find an internship, how to apply, what to expect. So after the learning inventory, we had to think to ourselves, what does a program map look like? Some things to keep in mind. First of all, for physics, it's going to look nothing like yours. You have different constraints. Physics is somewhat prescriptive, but not completely prescriptive. And of course, there's programs on campus that are completely unprescriptive. So everybody's will look different. This is just an example. We took the results of our learning inventory and we combined that with an up-to-date inventory of the requirements for all of our transfer partners in the state. And we came up with a rough draft of a program map for physics. So this map lays out what a full-time student might take and when. We started from Math 76 since we realized that our students are not coming to us at college level math. Most of them are starting at pre-college level math. We didn't draft what a part-time or evening map would look like, but that is something we need to do in the future. So I used an online tool called Lucidcharts to make this program map. Yours might look different. You might have it in, you might do it in Google Docs or Word or PowerPoint or something. So for physics, math is really the backbone of our advising flow. We start advising by asking students what math class they're in, and the rest just flows from there. So here in the middle, I've got all the math classes starting with Math 76. Once a student hits a certain point in math, they can start in on their physics classes. On the left here, I've got a couple notes. If a student is going to some transfer institutions, they have to take chemistry. If they're going to others, they have to take computer science. I also added a little note in the bottom there that most careers that stem from a physics bachelor's degree involve programming in some capacity. And so when we advise students, we like to let them know, hey, you're going to have to write code at some point. Would you like to teach yourself or would you like to take a class? Aside from the math classes, I've got a bunch of boxes in purple, and those represent classes that can be taken in any order. Although there is a note at the top that says College 101 and English 101 should happen as early on as possible. But the other classes, tried to sprinkle them strategically so that they're covering the distribution requirements slowly over the course of their degree, and they get some variety in classes instead of just all STEM all the time. I've got these pop-up boxes with suggestions for distribution requirements, and these are suggestions that largely come out of our learning inventory. Some students come to us and they have really strong ideas already about what they want to take for classes, but a lot of the time they don't really know what to put in these spots. And so we have these suggestions based on our discussions from the learning inventory on students' long-term goals. So for that second communications class, we suggested public speaking, English 102 or English 103, because all of these classes are going to give our students critical skills in communication. For social science, we suggested classes from several different disciplines. A lot of physics work involves interaction with government agencies, so we listed a couple useful poli-sci classes. We also listed some classes that'll help students understand other cultures, since physics and STEM are really international endeavors now, and it's impossible to work in those fields without heavy interaction with folks from other cultures and other countries. There's a couple classes we thought might be especially helpful in broadening our students' experiences with critical thinking in a non-physics setting. And looking further down the road in their careers, we felt it would be beneficial for them to understand economics and to understand ethics, so that when they're making big decisions and hopefully leading change in their field, they can do that with equity in mind. In thinking about humanities requirements, we felt art was a really important area for our students to get because it hits a lot of critical things that can cross over and broaden their knowledge. We also wanted to relist some of those communication classes because we would like them to cover as much of that as possible. In creating this program map, we realized it's hard to address equity fully with just the courses. So our conversation involved a lot of non-academic supports, and it involved discussions that should happen during advising that go beyond, here's what classes you should take. We realized we need to start having conversations about careers, about building a resume now, about applying for internships, about seeking out support services like TRIO and MESA and the Tutoring Center so that students don't end up taking Calculus 1 4 times, about joining a club so that instead of feeling like a person who just takes classes here, students can feel like they're part of this college and start to feel like they're part of the physics community. So I think this program map was a good start to helping us rethink our work in advising in terms of students and their ultimate goals for themselves, but I think it's important to note that this is just a start. There were a bunch of things we wanted for our students that don't necessarily exist at EVCC or don't exist in a consistent way. Like we know there are a bunch of classes that offer some of the knowledge, skills, and abilities and high-impact practices our students need, but a lot of that is teacher dependent, so we didn't necessarily feel comfortable putting those courses down on the map because their SIFs don't necessarily list out those HIPs or KSAs. We identified that we wanted our students to see how physics connects to other disciplines, and in general, how disciplines relate to one another. That's a big part of what it means to have a liberal education. not just making students take classes from a bunch of different areas, but really challenging them to see that those subjects are connected and to see how they're connected. We don't have many learning communities on this campus, so this is not something we could just jot down as a course right now, but it's something we're thinking of for the future. And this all goes back to that concept of equitable achievement as being more than just grades, but having a well-rounded education. In thinking about our students' futures, we also thought about leadership skills. Right now, one of the best places for students to get those leadership skills is getting a job in student life, which is awesome, but it would be great if there were other opportunities for that. And in thinking about equitable engagement, and engagement here doesn't refer to classroom engagement, it actually refers more to civic engagement, because if you really want equity to work, you have to convey it to students and make them feel empowered to carry that equity work out into the world with them. STEM has a huge problem with equity, and people have talked about how to fix it for years, but maybe we should try having very direct conversation about equity in physics, like in a physics classroom, conversation about how people in physics classes do not represent people in the broader populace, and how physics really loses out because of that. We don't have those conversations currently with our students, but that might be critical in the future to make a real change in terms of equity in physics. Some of the other things to keep in mind are that most of our students are starting in transitional studies. So the folks in transitional studies, they're extremely passionate about helping students and working more closely with them, and they can really help us to close these equity gaps. And while we can't fix all the equity gaps just with classes, we also have all these people in student services who are super passionate about student success too. And these are people who can partner with us and provide a lot of the wraparound services that will get our students through, things that we can't provide as teachers and advisors. So I really also want to emphasize that this is the beginning of something, it is not the end. The biggest thing we have to do is to slowly change our institutional mindset. Instead of saying, well, we can't do anything about that, or it's beyond our control, or that's not my problem. When we see things that are a real problem for our students in their success, we need to ask ourselves, what can we do? Who can I talk to? Who can I bring into this conversation? What resources can we tap? How can we affect a larger change? Is there data that we can pull together to prove our case and get more people involved in this? And just to close, just a reminder that the program map is part of the Guided Pathways work, and the Guided Pathways work is very fundamentally equity work. I myself am really new to thinking about things in terms of equity, and I find myself having to do what our students do, and that's just practice. It was very easy for me to try and get through this whole learning inventory and program map without ever thinking about equity, and I really had to stop myself and go back and revisit this concept over and over again so that I was actually thinking in terms of equity. This is a new concept for all of us, and I just encourage everybody to practice this